Welcome back, friends, to this particular subject, Kinematics of Machines. So today we are going to learn about velocity and acceleration analysis again, that to graphical method only. This time I am going to teach you about Klein's construction method. So what is Klein's construction method? How it will be useful? So that's what we are. Basically, Klein's construction method is a graphical method which is used to find velocity and acceleration of a piston of a reciprocating engine mechanism, and it was given by Professor Klein. So please remember that this Klein's construction method is only suitable for slider crank chain or a reciprocating engine mechanism. It cannot be applied for any other mechanisms. So here in Klein's construction, what we do is the speciality of this Klein's construction is you can plot velocity and acceleration diagram on the configuration diagram itself. That means we are not going to draw all these configuration diagram, velocity diagram, and acceleration diagrams separately. These diagrams are done all together. Uh, so the same thing I am going to explain with the one problem. So the problem statement here is there is a reciprocating engine whose connecting rod length is given to you, crank length is given to you. So what you have to find out is you need to find out the velocity and acceleration of piston, and you need to find out the angular velocity acceleration of connecting rod. Not only that, you need to find out velocity and acceleration of point x. So what is this point x? This point x is nothing but a midpoint of connecting rod, and you need to determine all these values when crank has turned by 45 degree from inner dead center. So that's what has been given in the problem statement, and the speed of the crank is also given, which is mentioned as 200 rpm. Solve this problem. First, I have written the given data. The length of connecting rod is given, which is 20 centimeter. The crank length is given, which is 5 centimeter. The speed of the crank is given, 240 rpm. The orientation of crank is 45 degree from inner dead center. This much is more than sufficient to draw the configuration diagram. Using this, I have to draw the configuration diagram, but what you need to finalize first is the scale. So here if you see the values 5 centimeter and 20 centimeter are there, I have just reduced it by half. So I am going to consider 1 centimeter as 2 centimeter link length. So based on that, if I have to draw a crank, it should be of 2.5 centimeter. If I have to draw the connecting rod, it should be of 10 centimeter. So using this, I have drawn a configuration diagram. Many times I have explained earlier also how to draw a slider crank mechanism configuration diagram. In similar way you have to draw. So here first draw a horizontal line, locate any arbitrary point O. From that point O, draw a line OA which is inclined at 45 degree, and the length of this OA is 2.5 centimeter. Actual value is 5 centimeter. When you reduce to your scale, it will be 2.5 centimeter. Then use divider, place it on point A. You set it to an arc length of 10 centimeter. Why 10 centimeter? The actual length is 20 centimeter. So draw an arc. The point of intersection of this horizontal line and that arc will be point B, and connect point A and B. Complete the configuration diagram as I have shown here. So now using this, I need to draw a velocity polygon. So to draw the velocity polygon, there are two steps. First one is draw a line perpendicular to OB, and then draw a line or extend the line AB till it intersects with the line drawn perpendicular to OB. So that's what I have done. I have drawn a line perpendicular to OB and then extended this line AB till it intersects with O, the line perpendicular to O. So this point of intersection I am going to name it as B, and this OAB is nothing but velocity polygon. So you already got the velocity polygon, using which you can calculate the velocities of different links. Like in problem statement, what is mentioned is you need to determine the piston velocity. So piston velocity is nothing but the it is going to be indicated by length of OB. So as I told, OAB is velocity polygon, and for Klein's construction method, you need to use this scaling factor omega. That means if I have to find out the piston velocity, piston B's velocity VOB will be given as the length of OB multiplied by the scale which you have used, that is 2, and again multiplied by the scaling factor offered by the Klein's construction method. So this will give you the answer, and the answer for this one is 110 centimeter per second. You are getting the length of this OB as, you will get the length of this OB nearly around 2.2 centimeter multiplied by 2, which is the scaling factor which we have used, and Klein's construction scaling factor is omega, which is 2.1514. So omega you need to determine using n, speed. So 2 pi n upon 60 is the formula which you have to use to calculate omega. 240 is the RPM here, so multiply it by 2 pi and divide it by 60, you will get the answer at 25.14. So omega is equal to 2 pi n upon 60. This we already learned. Using that formula, I have calculated the angular velocity in radians per second, and based on that I have calculated the piston velocity, which comes as 110 centimeter per second. Now the next thing what has been asked in the problem statement is, there is one point x on the connecting rod AB, and this point x is nothing but the midpoint of line AB. So for this point you need to determine the velocity. As we already know that the configuration diagram and velocity diagram will be proportional to each other. So this AB, the midpoint of this link AB, can be represented as midpoint of this edge AB. So locate that point. Locate the midpoint of this AB and then join that point and O, like this. So this OX gives the velocity of point x to me. How? Vox is equal to the length of this OX. Again, the scaling factor which we have used is 2, and again the scaling factor offered by Klein's construction method is omega. So use this formula, and if you measure OX, it is coming as 2.3 centimeter, and when you do the calculation, the answer comes as 115 centimeters per second. So that is the second question which has been asked in the problem statement. Now further questions which have been asked on the problem requires acceleration polygon. So I need to draw the acceleration polygon first. So to draw the acceleration diagram, you have to draw two circles. One circle taking radius as AB and taking point A as center, like this. So this is a circle whose radius is AB and the center is A. Another circle is taking diameter. Please remember the diameter of the second circle is capital AB and the center is midpoint of connecting rod. So here it is point X. So draw a circle of diameter AB and taking midpoint of connecting rod as a center. Now the point of intersection of these two circles should be joined by a line. So here one point of intersection is there, another point of intersection is here. So join these 2 points by a line. So the point of intersection of this horizontal line and this line, this point I am going to call it as B, and this point, the point of intersection of this line and connecting rod, that point I am going to call it as B dash. So B dash and B I have located. Now this OAB dash B is nothing but the acceleration polygon. One more thing what you have to do is connect A and B. So this AB is the resultant of AB dash and B dash B, that is radial acceleration and tangential acceleration. AB dash is radial acceleration. Please remember, in this acceleration polygon OAB dash B, AB dash represents radial acceleration, BB dash represents tangential acceleration. So AB dash B is acceleration polygon with scale omega square. So as I have mentioned, the scaling factor for Klein's construction in velocity polygon is omega. For acceleration polygon, it is omega square. Now, the next thing is what has been asked is you need to find out the angular acceleration of connecting rod AB. So if I have to find out angular acceleration of connecting rod AB, I need to calculate tangential acceleration of connecting rod AB. Why? The ratio of tangential acceleration and the length of this link gives me angular acceleration. So you already know tangential acceleration is given as R alpha. Now I need to find out the alpha for this connecting rod. So I need to know tangential acceleration. When I divide it by length of the link, I will get the uh, angular acceleration of this link. So for that, uh, what I have to find out is tangential acceleration, and that is represented by BB dash. So measure BB dash and apply this formula. The tangential acceleration of connecting rod AB is given as BB dash which is the length of this link, multiplied by 2. Why? The scaling factor which I have used is 2 multiplied by omega square. So 1.8 into 2 into omega square is 25.14 square. So this gives you the tangential acceleration, and it is coming as 2275.3 centimeter per second square. Now what I need to find out is angular acceleration. So angular acceleration is the ratio of this tangential acceleration divided by length of the link AB. So alpha AB is equal to 227.5 divided by AB. The length of the link AB is 20 centimeter, which is connecting rod length. So calculate the answer. You will get it as 113.75 radians per second square. So that is the uh, third question which has been asked in the problem statement. The last question is again for this point x, you need to determine the acceleration. So AB is the midpoint of x is the midpoint of AB. Similarly, in this acceleration polygon also, the midpoint of this AB will be point x. Locate that point, join O and that point x. So AOX is the length of this OX multiplied by 2 multiplied by omega square. So answer will be 2654 meter per second square. So that's how we need to solve any reciprocating engine problem using Klein's construction method. End of this particular section. Thank you. If you have any questions, please mail us at the mentioned email IDs. Thank you once again.